Hello everyone, welcome to 10-Minute Physiology. In today's video, I'm going to be telling you what compliance is, as well as how compliance plays into the physiology of our blood vessels. So with that, let's give it a go. So I would like to start off with a little demonstration describing to you what compliance actually is. So right here we have a balloon, and this balloon is connected to an air pump. Now this air pump, when it's turned on, will blow air into the balloon. Now attached to the air pump is a monitor, and this monitor is going to measure the pressure inside the balloon, which is right now 4 units, and the volume of the balloon, which is now 6 units. So let's begin this demonstration. So let's turn on this air pump, and when we turn on the air pump, air will flow into the balloon, causing it to expand. Now the new pressure inside the balloon is going to be increased because we have more air inside, and the pressure is going to be 6 units. The volume is also increased, and it went from 6 to 9 units. So how can we use this in order to understand what compliance is? Well, compliance is simply a mathematical expression used to describe how the volume changes for a given change in pressure. So it's calculated by dividing the difference in volume by the difference in pressure. So what we can do to calculate the compliance of the balloon is take the values that we have on this monitor and plug them into the equation. And when you do that, you get a compliance of around 1.5. So compliance, simply put, describes how much the volume of a container changes for a certain change in pressure. Now, an example of a compliant object is going to be something like a balloon, because a balloon can easily expand when you increase the pressure. And something that's non-compliant is going to be something like a steel tube, because when you increase the pressure inside a steel tube, it's not really going to expand because it's rigid. So in order to understand how compliance plays into our physiology, we're going to look at an experiment where we compare a steel tube to a vessel. Now, what we're going to be doing is we're going to be comparing the flow rates at differences in pressure. And remember that as we increase the difference in pressure, we increase the flow rate. So what we're going to do is we're going to bring in our steel tube, and we're going to generate a certain pressure difference, and we'll just call that pressure difference P1. So the pressure difference of P1 generates a flow rate of around here. Now, if we were to increase that pressure difference inside the steel tube, we would get a flow rate of around here. And if we were to further increase that pressure difference, we would get a flow rate of around here. Now, if you were to connect all of these lines together and extrapolate, what you would get is a nice linear relationship between flow rate and difference in pressure. Now, this is described well by Ohm's law of hemodynamics, which basically states that the flow rate is equal to the difference in pressure over the resistance. Now remember, this line has an equation format of y equals mx plus b. So the y in this case is going to be the flow rate, the x is going to be the difference in pressure, and the slope, which is m, is going to be 1 over the resistance. So the slope is 1 over the resistance. Now what this graph is telling you is that inside this steel tube, the resistance is constant. And the reason why we can say that is because the line here is a nice straight linear relationship. So the slope is going to be constant, therefore the resistance is constant. And this should make sense because resistance is going to be indirectly proportional to the radius, and since the radius inside a steel tube is not changing, then the resistance shouldn't be changing either. So now let's do the same thing but with a vessel. So let's bring in our vessel and generate a certain pressure difference. So when we generate the first pressure difference, we get this flow rate. If we do it again by increasing the pressure difference, we get this flow rate. And if we do it again, increasing the pressure difference, we get this flow rate. And if we connect all of the dots together and extrapolate, we get this relationship. So the first thing that you should notice is that the relationship is no longer linear. And the reason why has to do with the slope. So the slope is still 1 over the resistance, but the key thing to take note of is that inside the vessel, unlike the steel tube, the resistance is changing. So the resistance is not constant, and it's causing the slope to not be constant. So why is it that the vessel doesn't have a constant resistance. So why is the resistance changing as we're increasing the pressure inside the vessel? Well, it's because unlike the steel tube, the blood vessel is compliant, and this means that as the pressure increases, the blood vessel can expand. Now remember that whenever something expands, it decreases the resistance, and this is because the resistance is proportional to 1 over r to the fourth, where r is the radius. So as we increase the radius, we greatly decrease the resistance. Now, how does the idea of compliance apply to arteries and veins? So in order to understand this, we're going to look at the aorta and the vena cava, and we're going to compare how the volume changes at certain pressures for both vessels. So this graph is going to be for the aorta, and this graph is going to be for the vena cava. Now, when you plot the different volumes at different pressures, what you're going to get for both of these vessels is something like this. So the first thing that you should notice here is that the slope of both of these lines is going to be dV over dP, so the difference in volume over difference in pressure. And this is the compliance. So the steeper the line here, the greater the compliance. So the first thing that you should note here is that as the volume increases, the compliance decreases, and we can see this at the volume extremes here. So you can see as the volume starts increasing, the slope really flattens out, and you can really see it in the vena cava. The second thing that you should note is that the vena cava is more compliant than the aorta. And we can see this because the slope is steeper in the vena cava. Now, it's important to realize that veins are much more compliant than arteries. So how are our vessels compliant? So what makes them compliant? Well, the thing that makes our vessels compliant is going to be the elastic fibers. Now, in order to understand how elastic fibers work in our blood vessels, we're going to have to understand springs. So here is a picture of a spring, and this spring right now is in its equilibrium position. So this means there's really no net forces being exerted on it, it's just at rest. Now, we can describe springs by using Hooke's law. So Hooke's law basically describes how much force you need to apply to increase or decrease the length of a spring. So F in this equation is the force on the spring, K is the spring constant, and X is the displacement of the spring. So we can see here that the displacement is the difference between the new length and the equilibrium position. Now, if you were to solve for the displacement in the Hooke's law, what you would get is that the displacement of the spring is going to be equal to the force exerted on the spring divided by the spring constant. Now, the spring constant is what defines how strong a spring is. It basically describes how hard it is to stretch or compress a string. So the larger the spring constant, the harder it is to stretch it. Now, inside our vessels, we have two different types of elastic fibers, or two different springs. The first is elastin, and the second is collagen. Now, elastin has a lower spring constant than collagen, and because it has a lower spring constant than collagen, elastin is much easier to stretch. Now, therefore, as elastin increases and collagen decreases in our vessels become more compliant. And as elastin decreases and collagen increases, our vessels become less compliant. Now, this balance between the proteins of elastin and collagen is actually what causes atherosclerosis. So atherosclerosis, or the hardening of arteries or stiffening of arteries, is due to the fact that as we age, the collagen levels in our blood vessels increase and the elastin levels decrease. So therefore it causes our arteries to become stiffer, which can therefore lead to hypertension. So in summary, compliance describes how easily the volume changes with a certain change in pressure. We also saw that our vessels, unlike a steel tube, are compliant, and that our arteries are much less compliant than our veins. We saw that compliance in our vessels is determined by the balance between different elastic fibers, and we also saw that collagen is harder to stretch than elastin. So I hope this video helped you understand what compliance is and how it plays a role in our physiology, and I hope to see you in the next one. See you next time.